All right. So far in the unit, we have talked about uniform distribution briefly. And last lesson, we focused on binomial distribution. So we're going to add another type of distribution on, and we're going to be talking about hypergeometric distributions. So just like binomial distributions, there's a few important pieces that we need to ensure are happening before we can determine if a situation can be defined by hypergeometric distribution. So for a situation to have hypergeometric distribution, all trials of my event must be dependent. This is the most significant difference between our binomial distribution and our hypergeometric. So when we get a situation, we want to think to ourselves, are my trials independent or dependent? Now, similar to our binomial distribution, we only have two possible outcomes, success or failure. Now, we need to decide what is a success and what is a failure, and we will work on defining that just so it's really clear as we work with this distribution. Now, to get started, we're going to do an example, and we're going to do an example that we've done a ton of times. So not this exact example, but very similar examples have been done before. So we're going to use Unit 2 concepts to solve this question. And then I'll show you how it is connected to the hypergeometric distribution and how we can use that distribution to solve the same thing. So here's our situation. We have 10 doctors and 6 nurses. We want to determine the probability that a 6-member committee is formed that includes 4 doctors and 2 nurses. So we're going to do this using our Unit 2 material. So if we look at our question, there are 10 doctors that are eligible, and we want to choose 4 of them. Then there are 6 nurses eligible, and we would like to choose 2 of them. So let's determine the probability of this happening. First, we determine the probability of our sample space. So this would be how many ways I can choose the committee with no restrictions at all. So I have 10 doctors, 6 nurses, so 16 people total, and I have to choose 6 of them to be on this committee. Now for the number of ways, I can choose 4 doctors and 2 nurses, the event that I'm looking for. So we want to choose exactly 4 doctors. So out of the 10 doctors, I'm going to choose 4 of them to go on this trip. So I choose my 4 doctors, and I need to choose my nurses. So out of the 6 nurses, I want to choose 2 of them. Now that I've put that together, I can find my probability of my event, which is 4 doctors and 2 nurses. So to find that, I take my number of ways my event can happen, 10 doctors, choose 4 of them, and 6 nurses, choose 2 of them. And I divide this by my sample space, so the number of ways I could choose this committee with no restrictions at all. And there are 16 people, and I would like to select 6 of them. So now if I put this into my calculator, I will get 10 choose 4 multiplied by 6 choose 2. I will get 3,150 in the numerator, and 16 choose 6, 8,008 in the denominator. And then I can just divide that, and I get 0.3934 or 39.34%. So we have done questions like this before. where we find the number of ways our event can happen, and we divide this by our total number of ways any outcome can happen, or our number of ways our situation can occur with no restrictions at all. Now, this situation here is a perfect example of a hypergeometric distribution. So we've actually used hypergeometric distributions before. We just didn't realize we were doing it. So what we're going to do is we're going to look at the equation for a hypergeometric distribution, and then we'll look at this question again and see how the two are connected. So here's our formula for a hypergeometric distribution. So I'll give everybody a second to write it down, and then we'll talk about what each of the things mean. So give everybody a moment. It is a little bit long, and then we'll talk about how to use it. Okay, so if you're still writing it down, that's not a problem. I'm just going to go through exactly what these pieces mean. Now, as we start to use this in examples, I'll break down how to use it, what it means in a little bit more detail, especially going from a word problem to this formula. It is a little bit of an overwhelming formula, so we'll definitely break it down after this. So we have our probability of our random variable x is equal to A choose x, where A is my number of possible success outcomes. X is my number of successes that we're looking for. Then we multiply that by n minus A. So n is my total number of possible outcomes, so that minus the number of possible successes. Choose R minus X, so the number of dependent trials minus the number of successes, all divided by n choose R, which is the number of total possible outcomes, choose the number of dependent trials. So that is a very overwhelming formula with a lot going on, but let's break it down and I'll show you what each of those pieces mean in the context of the example we just did. So for the example we just did, we need to define what a success is. Now, we just use the term success or failure because we either have a situation happening or it is not happening. So sometimes it doesn't necessarily mean that something has failed, it's just categorizing two events into two different categories. Now, for this particular example, let's define a success as having a doctor on our committee. So that's what we're looking at. And each time I choose a person for this committee, that is a trial. So I choose the first individual. Are they a doctor? Yes or no. I choose the second individual. Are they a doctor? Yes or no. And I continue this process for all 6 places on this committee. Now, because after I choose the first person, it changes the probability of getting a doctor for the next choice, it means that these are dependent trials. Therefore, it's a hypergeometric distribution. So what we can do now is we can determine these values down here. So first is n. N is the number of total possible outcomes. In other words, the total number of people I'm selecting from. Now, because we have 10 doctors and 6 nurses, that means I have 16 people total. And that is what my n value is. How many people do I have in total? Now, my A value is the number of possible successes. Now, this is referring to how many individuals fit to the group that I would consider a success. How many individuals do I have to choose from that would make a successful outcome? In this case, because we've defined choosing a doctor as a success, it means there are 10 possible ways we can have a success. Now for R is my number of dependent trials. Each time I choose an individual to be on this committee, it's a trial. So I pick the first person, I pick the second person, I pick the third person. Those are all different trials for this experiment. So because I have 6 people on my committee, I have 6 different trials. So R is 6. And finally, X is my number of successes. So I'm looking for 4 doctors on the committee or 4 out of 6 successes. That's what we're looking at. Now, if I look at my formula over here and compare it to this, it helps us to understand what's actually going on. So for the first piece, we did 10 choose 4. That is my A value here, my number of possible successes, and then how many I'm looking for. So there are 10 possible doctors to choose from, and I only want to take 4 of them. Now for the second part, because we still require 6 people on this committee, I have 4 doctors. Well, the rest of them then have to be nurses, is what that means. So that's why we have n minus a, which gives us 6, and r minus x, which gives us 2. Now, as we go as we go through future problems, we'll explain exactly what these mean in the context of the question more, which will give you a little more clarity. Now, for the denominator, this is just our sample space. So we take our n, which is the number of total individuals we can choose from, and then we take our r, which is how many individuals we're choosing overall. So once we go to some more examples, the variables here actually make a lot of sense. It's sometimes challenging just to identify them individually. So let's do just that. Let's go through and do some examples. Just after we find our expected value. Sorry, I just forgot that this part, we had to do this part too. So for our expected value, I just have on the side here a copy of the formula just so we can use it for the future questions. But similar to our binomial distribution, we also have a formula for the expected value. So if I know that I'm working with a hypergeometric distribution, I actually have a shortcut formula for the expected value. Of course, you could put together the whole distribution and take all of our outcomes and multiply them by their probabilities and add all that together and do it the long way. Of course you could. However, this is much more efficient. So if I know that I have a hypergeometric distribution, my expected value is RA over N. So I take my number of dependent trials, multiply it by my possible successes, and then I divide it by my total number of possible outcomes. These are formulas that you will be given on an assessment, but it is important to remember that this one is possible. Okay, so now what we're going to get into is we're going to do some examples, and the examples help out a ton in actually understanding what's going on here. So we're going to go through this first one together. We're going to break it down nice and slow. So here's our situation. We want to calculate the probability distribution. So that means the whole graph with all the outcomes and all the probabilities for the number of grade 12 students to be selected for a 3-member school committee if there are 8 grade 12 nominees and 6 grade 11 nominees. Now you'll start to notice a trend with hypergeometric questions is we often have 2 different groups and we're selecting them to go do something. So similar to the doctors, we have another committee here. You'll start to notice a lot of consistencies in these kinds of questions. So the first thing that we need to do is we need to define what a success is, because that helps us define all of our other values. So because we want to calculate the probability distribution for the number of grade 12s, that's going to be our success. So we're going to let a success be selecting a grade 12 student. There we go. So each time I choose a student for this committee randomly, If I select a grade 12, we're going to say, yep, that's a success. That was the outcome I was looking for. If I select a grade 11, we'll say, oh, that wasn't quite the outcome I was looking for. So now let's identify our values of our variables for our hypergeometric distribution. First, we'll start with n. N is the total number of students I am choosing from. So because I have 8 grade 12s and 6 grade 11s, it means I have 14 students total to choose from. So N is all of the people we are choosing from. So that is the whole group of people. Next is my A value. Now A is the number of possible successes. In this case, a success is choosing a grade 12 student. So I look and we have 8 grade 12s to choose from. So that means A equals 8. So this is the number of people in the success category. There you go. Hopefully breaking it down like this is helpful. Then we'll work through R. R is my number of dependent trials. So each time I choose a student to be on the committee, that is a trial. Then each time I do that, I determine, is it a success? Is it a failure? Each time. Now, because we have a 3-member school committee, we are selecting students 3 times. So our number of trials is 3. Now we want to have the whole probability distribution. Sorry, number of people being chosen. I realized I didn't write that. There we go. Now for our X value, because we're writing out a probability distribution, we want to write out all of our outcomes. So we could have 0 grade 12s on the committee. We could have 1 grade 12. We could have 2 grade 12s, or we could have 3 grade 12s on the committee. So those are all of our options. So once we have all of that lined up, we can start doing our probability distribution. Now, as we go through the probability distribution, I'm going to show you a bit of a different way to approach this. So you can take these values and fill them into this equation. And as we go through, I'll talk about what each thing means to give you a little bit more clarity on how to approach it, which I think will help a lot. So I'm going to start by drawing my chart because we need a full probability distribution here. Here we go. So we're going to look at all of our different values for X. So we can have 0 grade 12s, 1 grade 12, 2 grade 12s, or 3 grade 12s on the committee, and then the probability of each of these events happening. So we'll go through and we'll do this one by one. Now, as we go through it, you can absolutely, like I said, just take the values that are to the left of the screen and sub those in. But I think it's beneficial for everybody if we know where they're coming from. So let's first start by finding the probability of having 0 grade 12s. So out of the 8 grade 12s, I'm going to choose 0 of them. But we still need 3 people on the committee. So that means out of the 6 grade 11s, I'm going to choose 3 of them. Then we need to divide this by our sample space. So in total, we're choosing from 14 students, and we're choosing a committee of 3 people. So out of the 14 students, we need to choose 3. Then I just put this into my calculator. 8 choose 0, multiplied by 6 choose 3, divided by 14 choose 3, which is 0.0549. There we go.
I have a question.
Yeah, sure.
What's the where did you get that the 8 choose 0 and the 6 choose 3?
Yeah, no worries. So there's two ways you can think about getting this. This here, my X's is my number of grade 12s on the committee. So out of the 8 possible grade 12s, we're going to choose 0 of them. We want no grade 12s on this committee. That means out of the 6 grade 11s, would have to pick 3 of them on the committee because we still need to select 3 people. That's one way to think about it. Another way to think about it is if I use my formula up here, this thing, my A value is 8, so this is 8. My X here is 0, so I can sub that in. N minus A would be 14 minus 8, which is 6. R minus X would be 3 minus 0, which is 3. And then 14, choose 3. So it's up to you. You could certainly just plug everything directly into the formula, or we can think about the situation and what's happening there. Either works for you. So again, where this came from, we have 8 grade 12s. We pick 0 of them. That means out of the 6 grade 11s, we picked 3 of them because we have to pick 3 people for the committee. And then we divide this by our sample space, the number of ways we can choose the committee with no restrictions. Hopefully that kind of helps. And then we'll go through some more. So I hope that clears that up. We'll do a couple more, and usually that helps a bit, but this one is probably the most challenging distribution that we do. So the next one, we want to pick 1 grade 12. So how many ways can we have 1 grade 12 on the committee? So let's figure out how many ways that can happen. So out of the 8 grade 12s, we want to choose 1 because we need 1 grade 12 on the committee. Now, because we need to choose 3 people total, we'll have 1 grade 12, 2 grade 11s. So that means out of the 6 grade 11s, we'll have to choose 2 of them because we can only select from grade 12s and 11s. So that's the only way that we can pick all 3 people, with having 1 grade 12, of course. Then we divide this by our sample space. So we have 14 students in total, and we're selecting 3 of them. Then we put this into our calculator. 8 choose 1, 14 choose 3 equals divided by 14 choose 3. Oops, I typed that in wrong. 8 choose 1, 6 choose 2, divided by 14 choose 3. And that gives us 0.3297. All right, we'll do another one together. So for the next one, we want to determine the probability of having exactly 2 grade 12s. So out of the 8 grade 12s, we're going to choose 2 of them to be on the committee. But because we need 3 total students on the committee, that means out of the 6 grade 11s, we would have 1 of them on the committee. Then we divide this by our sample space, 14 students total, and we're selecting 3 of them. Once we have this, I can put that into my calculator. 8 choose 2, 6 choose 1, divided by 14 choose 3, which is 0.4615. There we go. And the last one, we want exactly 3 grade 12s on the committee. So out of the 8 grade 12s, we're going to choose 3 of them. That means out of the 6 grade 11s, we're going to choose 0, right? Because we only have 3 people on the committee. So if there's 3 grade 12s, there's no grade 11s. And we divide that by our sample space. 14, choose 3. So that will give us, just typing into my calculator, 0.1538. Now, because this is a whole probability distribution, and we've written out all of our probabilities for all of our outcomes, these should add up to 1. And there's a little bit of rounding error here, but they're pretty close. There we go. I got 0.9999, teeny little bit of rounding error, but not too bad. Okay, are there any questions at all about that? Okay. These do take a bit of practice too. So if you are finding a little bit challenging, don't stress, you'll keep practicing and it will really start to click. Okay, so we have one more quick example. So the school committee is now being opened up to include grade 9 and 10 members. The committee will have a total of 7 members now. This time around, we have 10 grade 12 nominees, 9 grade 11, 12 grade 10s, and 8 grade 9 nominees. What is the expected number of grade 12 members on the committee now? So some things have changed. Now, because we have the same situation, it's changed up a little bit, but in general, we're still choosing people for a committee. We still have a hypergeometric distribution. You're either a grade 12 on the committee or you are not a grade 12 on the committee. But we've changed it up a little bit. Now, because we are looking for our expected value and we know it's hypergeometric, our expected value can be found by taking R, multiplying it by A, and dividing by N. So let's find a few of these values. First is N. N is the total number of students that we have to choose from. So we have 10 grade 12s, 9 grade 11s, 12 grade 10s, and 8 grade 9s. So in total, we have 10 plus 9 plus 12 plus 8, which is 39 students to choose from. Next, we have R. R is our number of trials. Each time I choose a student for the committee, that's a trial. So I choose student 1. Are they a grade 12 student? Yes or no? Success or failure. Choose the second student. Are they a grade 12 student? Yes or no? Success or failure. So because I have a total of 7 members on the committee, my R value is going to be 7. Finally, we need our A value. And our A value is the number of possible successes. So how many grade 12s do I have to choose from? If I look here, I have 10 grade 12 nominees to choose from. So my A value is 10. Once I have all of that, I can sub it into my formula. So I'll have 7 times 10 divided by 39, which would be 1.8. Now remember, although we can't have 0.8 of a person, of course, it just means if I randomly selected this committee over and over and over again, on average, I'd have 1.8 grade 12s. So usually I'd have 2 grade 12s if I picked this randomly over and over, but sometimes I'd just have 1. So that is our lesson. Are there any other questions at all?
Wait, can we use this equation for question 1? Like, is that still